So I've mentioned a couple times before that my first introduction to computers and CPU architectures is with the 8085. And specifically, that was in a college course regarding microprocessors and microcontrollers. And so in that course, I had a little trainer device, had a keypad and some numbers. You could view the contents of memory, view the contents of registers. You basically mess around with this CPU and this CPU environment here. And they use that to teach us how how a general CPU or how a general computer works. And the CPU of choice was the 8085, so that was the one that they taught us how to use, and that's why they gave us so much as far as documentation is concerned on the 8085. And so that was the CPU that I first grew accustomed to, and that's the one that I learned the most about. And this CPU fascinated me. The fact that this little piece of silicon could perform all of these computational steps to do some really impressive things. It really kind of captured my imagination there. And so that's kind of what kickstarted my journey into computational redstone, because I would use that as sort of a means to explore, how might this CPU work? Because obviously the documentation would tell us what the CPU did, but it didn't really tell us how it did it. And so that was kind of left up to my own interpretation. And I've learned a lot over the course of these years, playing around with different CPUs and different CPU architectures. And obviously I've gotten very good at being able to take complex instruction sets like these and turn them into complex behaviors. And my tool of choice has been the state machine. But I'm still very curious how Intel decided to do that sort of thing, how they managed to get this chip to take this really, I wouldn't say super complex, but pretty complex instruction set and turn that into tangible behavior. And so in order to figure this out, I figured we'd do two stones with one bird, because on the one hand, I would like to know exactly how this CPU managed its timing. And two, I think it would be cool to have a transistor-accurate recreation of the 8085 in Minecraft. And so in order to actually achieve this goal, I'm going to have to study the chip a little bit further. Now, unfortunately, there is no documentation, or at least no public documentation, as to how the 8085 works exactly. And that's where reverse engineering comes in. There's actually resources online where you get the actual die image. This is the die image of the Intel 8085, or at least I think this is a competitor. I think this is an AMD version of the 8085, but I don't have anything else to go off of, so I'm just going to have to go off of this. I'm going to have to assume that this is probably as close to the original design as Intel intended it. So this is what I've got, and obviously, this is cool and all. It's really fascinating to see the transistor view of this chip and see how everything kind of comes together. And if you're curious what all of this means, it's actually really interesting. There's basically three layers that you have to concern yourself with. There's the blue wires, which is the metal. There is the red, which is polysilicon. And then there's green, which is diffusion. And then there's also these orange boxes. These are vias. And there's also a buried layer. You might see one here or there. Yeah, this magenta is the buried. And basically the way this works is vias connect metal to either polysilicon or diffusion. As far as I can tell, it doesn't connect to both at the same time. But if you need to connect diffusion and polysilicon, use the buried layer, so these two bodies of pixels are connected because there's a diffusion layer there. And anytime you see polysilicon passing over diffusion, that's a transistor. So these two bodies of diffusion material are separated because there is a bit of polysilicon passing over it, making these transistors. And so all of this put together creates this, basically creates the 8085 in its entirety. Now, reverse engineering this sort of thing is a very, very large task, and fortunately, there are resources out there that have already done a good majority of the work, that being Ken Sheriff at the Righto blog. I'll leave a link in the description. He has a lot of really cool information just going into smaller details like hidden flags, how the ALU works, things like this. And then there's also the Pasterizer's blog, which is very minimalistic, but he still has some very useful information as well. For example, this is a very detailed table of the register timing ROM that's located inside the CPU. It's basically one of these giant tables here. I don't know if you can see what I'm looking at there. Just one of these. There's 6 of these tables, and these are all responsible for the timing. And he basically goes into the detail of all 6 of those ROMs. So obviously there's a lot of work that's been done, and I do have a collection of some of the reverse engineered circuits that they have put together. Only problem is what they've done is pretty incomplete. They've only reverse engineered so much of the chip, and I don't know how much of this is done. And so if I want to actually build this chip myself, I first have to understand how it works. I can use these blogs to figure out how the majority of it works, but there is going to be a portion of the chip that I'm going to have to figure out how it works myself. Now, what portion of that chip needs to be reverse engineered myself, I'm not entirely certain, because unfortunately, I don't have any references for where these circuits line up. So what I've been doing is I have been marking on the actual die view itself circuits that have already been figured out. And I figured what I do is I just draw these out, and as I draw them, that'll give me a visual indicator of which part of the chip has been reverse engineered. And then whatever doesn't have a marking over the chip, I can just reverse engineer myself. Now, there is a problem with this approach here. Obviously, having all of these lines scattered across all of these lines, it does clarify things, but doesn't make it clear what portion of the chip is part of what circuit. What's more is there's also lines that are going throughout the chip here. For example, you can see these 2 wires right here. These actually span the entirety of the chip, because these are the clock signals, basically, phi 1 and phi 2. So that is what controls the timing. That goes all over the CPU, but you wouldn't know that at a glance. There's no visual indicator. So not only that, but this whole process of just drawing it out manually, it's very time consuming. So my second approach that I tried was just a blackout system, where each circuit, I basically just get a rough idea of where it exists and I just black it out. And then I also did some attempt of keeping track of signals here. You can see some of these wires are a different shade of blue. And that's, again, the phi 1 and phi 2 signals. So that sort of helps with identifying the signals going throughout the CPU. But this is still confusing. I mean, obviously, I still don't have an indication as to what circuit this is, apart from just, the layers that I've got. I basically have to blank it out. No, first attempt I got it phi 1, phi 2. So this is the phi 1, phi 2 circuit, but you wouldn't know that right off the gate. So there's that problem. Again, there's also the issue of identifying these circuits. Again, the light blue and dark blue sort of helps, but there's only so many shades of blue that I've got. And if I use any other color, it could get pretty confusing pretty quickly. So obviously this isn't a great solution. And so to aid with this, what I really need is a tool that can help keep track of a lot of these things. What I basically need is, one, some kind of a program that allows me to draw and doodle over these circuits so that I can try and figure out what's connected to what, like I've got right here. But then once I've got that figured out, be able to select all of these wires basically and turn them into their own circuit that I can either fade out so that they're not, in focus, or just completely hide entirely. And then the other thing I'd like to be able to do is select individual wires like this and annotate them. So like I said, these wires right here, these are phi 1 and phi 2. I'd actually like to be able to select these and say, label this phi 1, label this phi 2. And that way, if I ever encounter that wire anywhere in the circuit, I can hover over it and see, oh, this is phi 1, this is phi 2. It's the idea being here that it would take care of a lot of the notes that I have to keep in my head or in a separate document to make it easier to figure out what the hell it is I'm looking at. And so I figured, if that's the kind of tool I need, obviously I don't think that there's anything that exists like that out there on the internet, so I'm likely going to have to make it myself. And so what I did over the last week here was just prototype that. So this is basically a first attempt here. What you're seeing here is not an official circuit. This is basically just a test circuit that I put together. But basically what you can do is you can load in a bunch of layers like this. This is, again, similar to this. We've got 5 layers to this set of images. We've also got 5 layers here as well. Blue representing the metal, green being polysilicon, or sorry, red polysilicon, green diffusion, yellows being vias, and magentas being the buried layer. And so what I've got is I basically just built a test circuit using a bunch of these images, loaded them into this program, and during my development, these acted as my tests. And so what I've got here is just, it's not much. It's just a very, very basic demo, but it's a pretty important demo because one of the biggest challenges with this is just identifying what's connected to what. Obviously, this is nothing more than a bunch of pixels. How do you, decipher what's connected to what? Obviously, you can do so visually. You can see that, green is connected to itself, blue is connected to itself. Anytime you see the via that connects the blue to the green or the blue to the red or things like that. But obviously, in order to, for a computer to figure that out, it needs some kind of image processing capabilities. And so that's what this is right here. I've basically got that set up. So two basic features. One is the ability to pan, the other is the ability to zoom. So not terribly much there. But the big thing here that I want to show off is the ability to select circuits. And anytime you select a body of pixels, it's going to select everything that's connected to it. Doesn't matter where on that body you select it, it's going to select it. But what makes this special, and what makes this, I think, noteworthy, is the ability to select from other layers if they overlap. And so you can see here I've got one circuit selected. It's going from this piece of metal through the via into the diffusion layer, through another via to metal, to another via to polysilicon, then a final via into the last bit of metal here. And then these two pieces of metal underneath these extra bodies here, because there's no vias connected, they're not selected. And of course, there's other rules involved here. For example, like I said, I don't expect there to be any vias that connect both diffusion and polysilicon together. I would expect that to happen only in the buried layer, but here I've got one test that has diffusion and polysilicon passing over each other with a via underneath, and you can see when you click on one side, it only selects that one side or the other. It doesn't select both because they're not connected. So it recognizes that there's no connections there. Likewise with transistors, here we've got a solid body of diffusion material. And so if I select the metal, if this program were to see this as one body, it would select all of this circuit right here. But you can see when I press the metal, it only selects one side because it recognizes that because there's polysilicon passing over the diffusion, this is a transistor, and that makes it two separate circuits. So I can select one side, I can select the other, I can also select the actual gate, and those all count as three separate circuits. Now, if you're curious how something like this works, you're in luck because I actually do want to show you how this works. The solution that I came up with is actually, I'm quite proud of it, and I would like to share it with you. But before we go into the code, I think it's probably better to actually explore the theory of operation here, because a lot of this actually has to do with mask arithmetic. And so the way this works is anytime you load a layer into the program, it first takes the image, it loads it, and then it puts it into a layer object. Now that layer object contains a few images, not just the source image. So it contains the source image, but then it also contains sort of a layer mask or a total mask is what I've labeled it. And the total mask is basically just the layer in mask form. And we'll see what all these masks are for later on. But then it creates another mask called the selection mask, and by default it's blank. But that's actually what we use to keep track of what wires on the layer has been selected. And then lastly, we have the individual wire masks. Basically, any wire that exists on any of these layers gets their own mask. And again, we'll see what those are for here in just a minute. And so when it comes to making a selection, the process begins by taking the mouse coordinates that the user creates when they click and turning that into what I call a search mask. It's basically just a normal mask with a single pixel indicating the user's selection point. And so the first thing that happens is that selection mask, or that search mask, excuse me, is applied to the total mask. And basically, if the masks do not overlap, you're going to get a result of nothing. If they do overlap, you'll get that single pixel back. So by overlapping them, we can see if the user has selected a valid circuit or not. And all I do is I just take that resulting mask, I put it through a function that searches for any white pixels, and if it comes back true, then there is in fact overlap. And so once we've determined that there is in fact overlap with the search mask, we then go through all of these wire masks one by one, and we check to see if any of them overlap. And if they do, we then take that wire mask and we add it to the selection mask. Now, the reason why we add it to the total mask instead of setting it to the total mask is because there could be other circuits in the image that need to be selected as well. For example, if we're selecting this circuit right here, you can see that there's 1, 2, 3 bodies of wires that need to be added to the selections mask. So we add that one, and then later on, if we need to add this one, we can add that as well. But in this instance, in this particular time during this cycle, the selection mask is just equal to one of these wire masks. And so what we can then do is we can then look at that layer's connecting layers. So because the metal layer connects to the vias layer, that's the only layer that we would then check. So we can then go to the vias layer, we can grab its total mask, and here's the kicker, is we can then use the metal layer's selection mask as the new search mask. And so what we then again do is we overlay the two, and if there's any overlap, we know that there is a via connecting to that piece of metal, and we can then start the process of adding it to its selections mask. Now from there, the vias layer is going to have a selection mask that basically looks like this. And what we can then do is take that selection mask and go to the diffusion layer or the polysilicon layer with that exact same selections mask used as the new search mask, and we can find any bodies of these materials that overlap and add those to the selection as well. But there is a problem with that, because even though the the vias is connected to the diffusion and the polysilicon, it's also connected back to the metal layer. And so what can happen is the vias layer might actually go back to the metals layer and research for any overlap. And because there was already established overlap to begin with, once it goes back, it's going to find that overlap and then start the process of reselecting that region of the metal layer. And that can cause a problem, because then what ends up happening is the metal layer selects the vias layer, which selects the metals layer, which selects the vias layer, and back and forth it goes. To solve this problem, before we check for overlap between the search mask and the layer's total mask, we first take the layer's selections mask, we invert it, and then we add it to the total mask. Once we do that, we can take the search mask that comes from the vias layer and we can AND it with the total mask, and so long as it overlaps something that's already been selected, we should not see any overlap. The end result of this, of course, is the search is stopped and the process returns, ensuring that there's never going to be an infinite loop. From there, it's basically just a case of moving up and down the layers, finding any overlap and adding it to the selections mask, and repeating that process until there's no overlap left. So when you start with the metal layer, you add the selected wires mask to the selections mask. You then move to the vias layer, adding any overlapping vias to the selections mask. Then to the diffusion layer, which adds any overlapping diffusion to the selections mask. Back to the vias layer, which adds the next via to the selections mask. And then back to the metal layer, which adds the next metal wire to the selections mask. And back and forth it goes until there's no more overlap and everything has been selected. Now there's two exceptions to this rule, and the first is at the vias. Any via has to have some metal underneath it, otherwise the polysilicon layer or the diffusion layer cannot connect to it. So there is a bit of logic there to check for that sort of condition, which is why when I clicked on these circuits, the via in the middle was never selected. The second condition is the transistors. I've said it already, but these transistors are basically made of a diffusion layer that's overlapped by a polysilicon layer. Now, that makes sense to you and I. We see the polysilicon passing over. We think these are three separate circuits. But the computer sees the diffusion layer as one solid chunk of diffusion material, so it could potentially see that as one solid circuit, but it doesn't. The trick then is to block out any parts of the image we don't want turned into a wire mask before that happens. And we can do that. In this case, I have the diffusion mask and the polysilicon mask. We can do that simply by ANDing them together. So if I AND the two together, what we're basically left with is any overlap, any parts of the diffusion circuit that is overlapped by the polysilicon. And so during the first pass, what we can do is we can turn all of these into separate wire masks, and what that will result with is basically wire masks that are just the overlap. What we can then do is we can invert the polysilicon mask And the end result is all the regions that are just diffusion material that's not overlapped by polysilicon. And so by doing these two passes and turning each of these into wire masks, what we're left with is, for every transistor, basically 3 wire masks, one on either side of the transistor, and then one where there's overlap with the polysilicon. And so feeding those into our algorithm here with all of our wire masks basically allows us to separate the transistor into 3 distinct parts that are each separately selectable. And so with that in mind, we can take a look at the code here, and hopefully this mess will probably make a little bit more sense. But what we've got here is we've got a class connections analyzers. And what that does is it first loads in the different layers and then sets up the connection logic as well as the requirement logic. Again, for the vias, it requires metal, as well as the separator logic, which is for the diffusion, it requires the polysilicon. And so that separator is basically used in that mask setup process. And then the requirement is used during the actual selection process. And so here we can see a dictionary listing out all the connections. Again, metal connects to vias, vias connects to metal, polysilicon, diffusion. You might notice that diffusion can actually connect to polysilicon. Likewise, polysilicon can connect to diffusion, and that's basically for the overlap regions. Again, if the two are overlapping, there's likely going to be a buried in between them, and that's going to connect the layers. But for the overlap where it's just a transistor, the region of the diffusion layer that's under the polysilicon is going to count as its own separate circuit. And so if you perform any selection on that region, that part of the diffusion is never going to be selected no matter what side of the transistor you pick. So I basically just allowed the program to connect that region directly, and that allows for that part of the diffusion layer to be selected when you select the gate part of the transistor or the polysilicon. And so all this does is it basically just loads in the images, creates the objects, creates the connections, and then sets up any special conditions that need to be set up for that sort of thing. And then the rest here is just boilerplate. Reset selection, check for selection, get layers. The select one, I think, is probably the only one that's interesting because, again, what we're doing here is we're taking the mouse position and we're turning it into a search mask, which we then push into the layers. Either if a layer is provided, we select that specific layer. If no layer selected, or if layer selection is none, we basically perform that selection search on all layers. And then looking at the layer class here, what we've got, of course, in the setup is the actual creation of the image, the total mask, the wires mask, or wire masks, I should say, and then here we reset the selections mask, which in the process of doing so basically just creates a new mask. So that creates all 4 masks, or 3 plus the wires masks, I should say. And then we have a few attributes, connections, and requirements. That's basically for the selection logic right here. But here we can basically see the process that was described earlier. What we can see here is during the selection process, we take a search mask, and then the first thing we do is we logic AND the total mask with the inverse of the selections mask. That's what sort of takes out of the total mask the parts that we've already selected, prevents that logical loop. That's basically the unselected wires. Then what we do is we check for overlap by logic ANDing the search mask with the unselected wires, and then we check to see if there's any white pixels. If there are no white pixels, we return right there. We don't continue any further. If there are white pixels, though, that means we know that there's overlap, and we need to figure out which wire masks need to be added to the selections mask. So that's what all this does. It basically just goes through for each wire mask and wire masks. It looks for any overlap, again, just by logic ANDing the search mask with the wire mask. Looking for white pixels, of course. And then here we also do a check. We check to see if the requirements equals none, or if the requirement layer has overlap with the overlapping wires. And if either of those are true, then we add the wire mask to the selections mask. And then after all that's done, then we go through each connection and we tell it to do the same thing using its own selection mask as the new search mask. And then lastly, there's just a method for actually drawing to the screen. Obviously, we need some kind of visual indicator. I'm using tk-enter. Obviously, there's some disadvantages to that. I'll get to that in a sec, but this is basically just the logic that is used to, one, draw the image to the screen, and two, also highlight certain regions of it depending on the selections mask. And so I think the last function to go over here that's of any interest is this load images and generate masks. This is basically what the layer class uses to generate the image, the total mask, and the wires masks, or wire masks, I should say. And that just takes an image path and that separator argument, as I mentioned before, loads the image in RGBA mode, creates the total mask just by copying the image and then turning it into a binary image. Pretty straightforward. Then what we do is we check to see if there's a separator argument. If there's not, we only do one pass of creating the wire masks using the total mask. And if there is a separator argument, we then do that first pass with a normal overlay and then a second pass with an inverse overlay. And then that creates all of the separate parts of the transistors that are required. And then the internal function here, create wire masks, that just takes a mask of some kind and then just separates it out into the individual mask images. And this uses a library called skimage or skimage, more specifically the measure.label method. I'm not entirely certain what this does. I actually had ChatGPT help me figure this part out because I couldn't figure it out for myself. It seems to work. It seems to be pretty quick. So I'm just going to leave it as that. But basically all it does is, like I said, just takes a mask of separate bodies of pixels and then separates them out into individual images. Now, I think the one concern I would probably have with this whole function right here is obviously, creating a separate image for every wire in every layer. That's a lot of images that has to be created. In particular with the original images for the 8085, those are some pretty big images. They're about 7200 pixels by 5300 pixels, and obviously one image for every wire is going to result in a lot of images. I think my only saving grace here is the fact that each one of these images is what's referred to as a binary image. So basically each pixel is represented by a single bit, which means that the size of the images should be a lot smaller than the original images. That's the idea anyway, but even still, there are some shortcomings to this program. And one of those shortcomings is just speed overall. Obviously, you can see a little bit of jitter anytime I move this thing around. And that was originally a lot worse. During the process of developing this, I actually had some functions that used a lot of nested for loops, and that slowed the program down horrendously. The use of these masks and everything actually does speed up the program quite a bit, but you can see it's still very slow. However, I don't think it's the number of images that are stored in RAM that's the cause of this, nor do I think it's the number of back and forths between layers that's causing the issue. The biggest slowdown of all this is actually just drawing this to the screen. If I actually go ahead and zoom way out, you can actually see that it's a lot more responsive versus if I zoom way in. Oh, my computer's screaming. Oh, it doesn't like this. Yeah, it's a lot worse. So there's something about TK Enter. It doesn't like rendering images, particularly this big. If I get any bigger, it's going to cause problems. So that's obviously a problem that I'm going to have to overcome at some point. It's probably not going to be too early in the development cycle. I can live with it being a little bit jittery for during the process of developing. But when it comes to actually using this as a proper tool, I am going to want to get that problem figured out. And so I'm not sure if there's a better tool that I should be using to actually render these things. I've already gotten some feedback from friends saying TK Enter is not the best library to use. The other thing that I could do is I could possibly offload the rendering process to my GPU, though I'm not entirely certain how to do that. And then the third process actually is to just split the screen down the middle, have sort of a total view on one side. Obviously, it'd be the same size images, but zoomed really far out. That should shrink the size of the image small enough that the program should be able to render it just fine. And then on the right side, have sort of a zoomed in view. That's kind of a bug I'll need to figure out. But on the right side, just have sort of a zoomed in view. And so I could have a magnifying glass on the left side that I can move around and do my actual editing and selecting on the right side. And I think with a split screen like that, it should, the image sizes should be small enough that it shouldn't overload TK Enter too terribly much. I don't really know. I don't really want to prematurely optimize here, so at this point I'm just exploring options. Haven't really decided on anything yet, but if you have any suggestions on any ways I could improve this, feel free to leave that in the comment. So yeah, that's basically what I've got so far. It's not a whole terrible much, but I think that this is a significant step in the right direction. And personally, I think this is the largest step in the development process. The ability to select individual circuits based on connections, I think, is a huge step forward. And then from there, it should be a lot of just small tweaks to add little features. But again, we've still got a little bit of a ways to go. I still want to be able to label the individual connections. That'll probably be what's going to come next. Thereafter, it'll be grouping, and then group hiding or group modifying, as well as group labeling, and then, of course, the doodling, being able to doodle on top of everything and associate that with certain circuits or certain wire groups would definitely be helpful. So that'll probably be later on in the development cycle, though. So likely it'll just be labeling first, because that's going to be pretty straightforward. So yeah, that's what I've been working on. I think this will be an interesting little tool, and obviously when it comes to developing tools to help you perform tasks, there is a very big risk that the development of the tool can take longer than actually just performing the task. I don't think that's going to be an issue here, because as we've just seen, I've only been working on this for a little over a week, and I've already got some pretty significant progress made. So I think as far as developing of the tool is concerned, I don't think it's going to take too long. I also don't think it's going to take too much of of effort to actually get this to a point where I can actually use it. But that means that, I'm super excited to get to the point where I can use this tool to start reverse engineering the 8085, because the sooner I start that, the sooner I can actually get a comprehensive schematic view going, and then the sooner I can actually start turning that into a redstone computer. So I'm excited to see where this project goes, and I hope you'll join me on this journey here. I hope to try and get more videos like this, just short little updates, uploaded as frequently as possible here. With that said, though, I'd like to give a special thanks to the people who have pledged to support me on Patreon. If you'd like to support my channel and help me get to the point where I can actually make videos on a more regular basis, feel free to check out my Patreon. If you pledge just $1 a month, you get access to the Patreon feed, where I've basically been posting almost daily project updates. Here's one that I've got posted on the software that I just showed you here. So even just pledging $1, you gain access to this. You'll get a lot more frequent updates on what I've been working on, as well as the ability to voice inputs on what you think should be made, any adjustments you want, things like that. If you just want to be able to participate in the development process, then again, check out my Patreon, see if there's a tier that you'd be willing to pledge. Again, thank you for your consideration. The link will be in the description. And again, thank you so much to the people who have already pledged. You have made a world of difference for me, and I cannot thank you enough.